Good morning and a warm welcome to yet another Baltic Breakfast coming to you from Stockholm University. I hope you've all gotten a good breakfast and have some time to join us here when we will talk about eutrophication. We will today sort of focus on aluminum treatment of lakes and sea bays and whether or not this is a good tool in the combat for eutrophication problems. So let's focus on what are the opportunities and what are the obstacles. My name is Gun Rudqvist and I work as Head of Policy at the Stockholm University Baltic Sea Center. And it's us, the Baltic Sea Center, who organize these Baltic Breakfast. We are, of course, a research unit, but we also have a mission to try to bridge the gap between science and policy, bringing to you, in different methods, good research results that are relevant for different policy stakeholders. And we also run a field station, which is just south of Stockholm. It's well worth a visit if you come to Stockholm. So today we will talk about aluminum treatment in regard to eutrophication. As always during these Baltic breakfasts, you can of course pose questions, and we will definitely do our best to deal with the questions. You can see in the picture, you can see a Slido code, which is 22102, 22102. So either post your questions there or send us an email at ostersjocentrum.su.se. So we will get back to the questions after the presentation. And if we don't have the time really to go through all the questions, which is very often the case actually during these breakfasts, we will ask our researchers to write down answers and present them on our web afterwards, which is a great way of getting in touch with you guys. So please give us your names and how we can sort of get back to you with good answers. Well, let's move on to today's topic. Eutrophication of waters, of course, remains a problem. Nothing new there. And nothing new about the fact that phosphorus is vital for all living things, but also floods our waters. If there is already too much phosphorus in lakes and sea bays, is it possible then to bind phosphorus to bottom sediments using aluminium treatments? It has been used in lakes for quite some time and there are good results. But again, what are the benefits and what are especially the obstacles? We will look into that first, and there we will have Brian Huser, who is an associate professor from the Department of Water and Environment at the Swedish University of Agricultural Sciences, who will help us out there. And after that, we will sort of continue with the question about how about treating sea bays in the same manner? Is this possible or not? And Bo Gustafsson, who's an associate professor of oceanography and also the director of Baltic Nest Institute here at Stockholm University, and my colleague at Baltic Sea Center. He will tell us about a recent modeling study looking at Björnefjärden, which is a very enclosed sea bay here in the southern Stockholm archipelago. But let's start by giving you sort of the broad overview and a study that Brian and his colleagues has done by compiling lots of interesting research results about lakes. So please, Brian Huser, the floor is yours, and you can start sharing your screen.
Thank you. Is the presentation showing up?
Yes, it's showing. It's still not in presentation mode. Yeah, here we go. Fantastic.
Great. Okay. So once again, my name is Brian, and I'm going to give a more general overview of aluminum treatment and what we've seen with respect to longevity and effectiveness with this type of restoration measure. So aluminum has been used for almost 60 years now to restore lake water quality. One of the first lakes treated, or reported anyway, was Långsjön in Sweden. There are many Långsjöns. I think this one is in Huddinge. There have likely been thousands of treatments. Hundreds have been documented. There are over 100 treatments in the state where I'm originally from, in the States. Aluminum has been used for drinking water treatment for quite a long time. There there are two different types of treatment methods. Either the aluminum solution can be added to the water, where the mineral forms and precipitates to the sediment, or the mineral can be injected directly into the sediment. And this can have a positive effect on binding efficiency, which I'll mention later. But I believe this particular method, the sediment treatment, is only used in Sweden. So why do we use aluminum? Well, the main reason is there's excess phosphorus in the sediment that has nothing to bind to, so this phosphorus then gets released and contributes to eutrophication. Iron and calcium are two alternatives. Iron, however, releases phosphorus under low oxygen conditions, and calcium is better suited when pH is higher in something like a wetland, maybe. When you add aluminum to lakes, it forms a natural mineral, gibbsite for the most part, which is already found in soil and sediment. But a big question here is it possible to assure a long-lasting treatment? And the answer to this question is yes. And I'm going to talk about this, but I would also like to say that aluminum treatment is not the only measure to reduce internal loading in lakes, but today's talk is about aluminum treatment. So what is aluminum? I thought it'd be good to talk about what this actually is. It's the most common metal in the Earth's crust. We eat aluminum every day. It's found in things like antacids, baking powder, other things. It does not bioaccumulate, otherwise we'd be in trouble. It's up to 10% of the Earth's crust, so it's everywhere. It's often called a chemical treatment, this aluminum treatment, and I've done this before too. But that's wrong. It's actually a mineral treatment. So when we add this aluminum solution or aluminum salt to a lake, it forms an amorphous mineral directly after addition that either precipitates to the sediment or is injected into the sediment. This mineral begins to crystallize, as all minerals do, and this can affect binding efficiency again, which I'll talk about in a little bit. And here's a very old piece of gibbsite, very hard, similar or the same mineral. So how does the treatment work? So we're basically restoring the balance between minerals that bind phosphorus and phosphorus in the sediment. Here we have a natural lake, no excess external loading, very little or no internal loading of phosphorus from the sediment. There's enough mineral to bind that phosphorus in the sediment to keep it there. Here we have a lake that's had excess external loading of phosphorus coming to the lake for decades. That phosphorus has, for the most part, accumulated in the sediment. There's not enough mineral mass in the sediment to keep that phosphorus there, so it starts to be released and become its own source for eutrophication in the lake. So when we add aluminum, we're restoring that balance. So we're adding more mineral to bind that excess phosphorus in the sediment. This keeps the phosphorus in the sediment, and this internal phosphorus loading from the sediment returns to a natural level. So what are some of these factors that affect treatment longevity? Longevity of treatment has varied from weeks or a couple of months to over a century or more centuries based on modeling, where we still see good effects on water quality from treatment. But longevity is not a word that we should use. I've used it. I'm going to show you a paper with longevity in the title. But if external loading is reduced to a natural level, the longevity of the aluminum treatment, if dosed properly, is infinite. If you take care of both sources of phosphorus, that's it. And this is true for all methods that can reduce sediment phosphorus release to a natural level, not just aluminum treatment. That phosphorus stays bound to the aluminum mineral permanently and is eventually buried with new sediment, even if the longevity is short, but that new sediment then will contain excess phosphorus that then increases internal loading again if external sources have not been controlled. So here's this big meta study where we looked at 114 lakes and looked at the longevity and effectiveness of the treatment for improving water quality. So this figure on the left is a little bit messy here, but on the y-axis we have measured longevity, how many years, and it's a log scale, but it's from 0 to 100. And then we have predicted longevity. This is our model, so we could figure out what factors contributed to longevity of this particular type of treatment in lakes. And it's a pretty simple model, actually. It's aluminum dose. Generally, the more aluminum you add, the longer the longevity. Lake type. Shallow lakes tend to have a shorter longevity, but that's mainly due to the fact that it takes less internal phosphorus loading to create eutrophic conditions in shallow lakes. And then watershed area to lake area ratio. And this is basically a factor of external loading. So if you have a bigger watershed, you're going to have more external loading. And as far as we know, none of these lakes that were treated with aluminum had controlled external loading properly, or it hadn't gone back down to a natural level. So the bigger the watershed, the more external loading, the quicker internal loading will come back due to new sedimentation with excess phosphorus. And now these dark triangles here are lakes that were treated with aluminum that had shorter than expected longevity. And they all had medium to high biomass of benthic feeding fish. And these fish dig in the sediment. So what happens here is that they increase the sediment mixing depth, which increases the amount of phosphorus in sediment that can come out, reach the water, and cause problems with eutrophication. So I'm going to sum up here. This is kind of a summary, kind of a little bit of detail too. Aluminum is a mineral that is naturally found in soils and sediment where it binds phosphorus. A proper design of treatment is critical for achieving a safe and optimal longevity. You're going to use that word. So one of the things we need to make sure of is that during mineral formation, and only during this first stage, pH can drop due to formation of the mineral. And we want to assure safe treatment. And this is very easy to do with geochemical modeling. It takes just a little bit of chemistry background. So that's the first stage of design, which is critical. The second stage, which is equally as critical, is maximizing the binding efficiency. How much phosphorus that mineral can bind. This affects longevity, but also saves money. And so I'm going to show a figure here. It's grams of aluminum needed to bind 1 gram of phosphorus. On the left here, we have a poorly designed treatment where it took 20 grams of aluminum to bind 1 gram of phosphorus. This has happened in Sweden or close to it. It's happened in Denmark. It's happened in some other areas. This is not what we want to have. In the middle, we have the average. This is kind of what we expect when we calculate how much aluminum is needed. On the right side, we have a very good treatment, and it only took 2 grams of aluminum to bind 1 gram of phosphorus. So what does this mean? And we've done this before. We've seen this in some lakes in Minnesota we've been involved with. We've been able to achieve this very good binding efficiency. So on the left, if we have poor binding efficiency, what this means is if the ratio is 20 to 1, half that phosphorus in the sediment that can be released will not be bound to aluminum just due to crystallization of the mineral. If we look at the best case scenario, we can treat 10 times the number of lakes with the same amount of money. So yeah, this design is very important, and it's not being done everywhere. It's not being done everywhere in Sweden or Finland or the US. We do this as it's standard practice, but it's not being done everywhere, and I think it's something that needs to be obviously done. It's cost effective, saves money, and also improves treatment effectiveness itself. And of course, external inputs of phosphorus need to be reduced. If they're elevated, internal loading will come back. And good monitoring data and dynamic lake modeling are needed. We need to figure out which nutrient sources are contributing to eutrophication and which ones need to be reduced. Otherwise, we're just guessing. And in many cases, still, we're using something called mass balance modeling, which is just a calculation of phosphorus running to the lake. Then we estimate the internal load as what's left over, and we're basically just guessing. So I want to show an example here because I have a little bit of time of how this can affect the longevity or the success of a treatment. So a lot of people think this modeling costs a lot. When you go in and collect data, develop a model, it costs money. And in the beginning, it might seem that way. It's about 15,000 euros for an average lake size, 500 hectares. This is generally 2% of the restoration cost. And it's even less if you fail, and I'm going to show a case of this. The Vector chain of lakes. So on the right, I have a figure. It's a chain of 4 lakes, and in the beginning, from the 1960s to about 2012, many measures were done: dredging, fish removal, stormwater ponds at a cost of greater than 50 million Swedish crowns. No dynamic modeling was done. The biggest or largest effect was from upgraded wastewater treatment. That is not included in that cost. The lakes did not recover. Truman after dredging, saw an improvement, a large decrease in phosphorus, but it still wasn't close to the water quality standard for that lake. This is Söderberg Unicorn, 2015 in May, which is basically winter in Sweden, after 50 million crowns. 2012, dynamic modeling. This is a very complex two-dimensional model, so it cost a bit more. It was 4 lakes, but it was still only 5% of the cost before 2012 where lake restoration failed. It's going to be much less, including the cost for restoration measures now. If Aquatic meets goals, Söderberg Unicorn is close. We're not done with implementing all the measures there yet, so it will meet treatment goals. So that's all I have. Thanks for listening. I'm not sure if we take questions now or later, but that's my standard ending slide.
Thanks a lot, Brian. I will pose a few questions and then we'll get back when Bo has also given his presentation. This was really interesting, and it also shows what you told me in advance, how it's complex and how you need to plan your treatments. So what you're actually saying is that you recommend to planners who are supposed to go ahead with these treatments to plan and model. Is that correct, right?
Right, with respect to lake modeling, but also with respect to the actual aluminum treatment and how it's going to affect the lake.
So that really pays off to do that kind of work and spend that few money. You said 2 to 5% of the whole cost.
Right. Yes. And if you look at this Växjö chain of lakes, they spent 50 million Swedish crowns for basically very little effect because they did not model in the beginning.
So do you see this happening more and more now, sort of in the different contexts you have?
I think so. Unfortunately, I think the majority of lake restoration projects still do not do this dynamic modeling, which Bo is actually going to talk about, I think, here up next. So it's getting better, but we're not there yet.
Okay. And the modeling is available even for people sort of maybe working at community level or something?
Yeah, there are free models available. Of course, it takes some background knowledge in order to be able to run these types of models. But I give a course on this next week at SLU.
Okay, that's a good way. Why don't you sign up directly? Yeah.
Yeah.
Another thing that you stressed sort of at the end, and you mentioned now and then, was the external input. And it's your experience that has been a bit neglected and people go for aluminium treatment instead?
Yes, in some cases. I think when you're looking at lakes in the middle of Stockholm, it's cost prohibitive to, well, first you can't tear down people's houses or apartment buildings to build a wetland. There's just no place to properly treat external loading. But in other cases where there is, I think the aluminum treatment can be seen as sort of a quick fix. And it can work this way, but of course it's best to reduce the source of phosphorus, otherwise internal loading just comes back.
Of course, yeah, okay. I'm sure we'll get back to this. Thank you so far, Brian, and we will get back to you soon again. So Bo, let's move on to talk about sea base, enclosed sea base, and in this case Björnefjärden. So the floor is yours, and give us the interesting presentation about Björnefjärden, please.
Yes, thank you. Yes, so I'm a marine modeler, and the background to this is that there's been a project since around 2010 or something by the Baltic Sea 2020 Foundation in Björnefjärden, which basically tried to do all kinds of measures possible to restore this bay to good environmental status. And towards the end of that project, a couple of years ago, we had a discussion from my group with Linda and Emil that worked on this Living Coast project, whether we could do some modeling. And we took that opportunity to. So it's been me and a couple of colleagues working together with the Living Coast project, and we've also got funding from the Living Coast project for a postdoc working on this. So what they did was that they treated Björnefjärden with aluminum, all the areas deeper than 6 meters were treated, which is basically half of the area of the Björnefjärden. And they have performed and still are performing intensive monitoring of both water column properties, and sediment properties. And what they showed is that it really became significantly better in the bay after the treatment. But what I will talk about today is our modeling, which we could adapt this model and test this model based on all those observations that were done. So basically, Björnefjärden is very small fjord system. It's only 1.5 square kilometers. It's shallow, it's 7 meters depth, but it has some deep holes that are deep down to 24 meters. We modeled this with an adaptation of our Baltic wide model, and we were kind of surprised that it actually worked to go from the Baltic Sea scale to the small scale relatively easily. It has an exchange with the so to say open sea. It's another Nämndöfjärden outside, but it's much more open. And it's a very narrow channel. You can see on this satellite image, you can see the boats there. You get a feeling of how narrow this contraction is. But we know pretty well how to model this kind of exchange. And there's also been part of this extensive monitoring program, there's been flow measurements in the straits as well, so we could validate the model exchange. These are just some what we call time depth plots. So you have time on the x-axis and a depth scale at the deepest location in Björnefjärden, and it shows temperature on the upper right, oxygen lower right, and phosphate to lower left. And as you can see, you have a very strong temperature stratification. There's also a salinity stratification that I don't show, but that also is manifested in the oxygen where there is significant oxygen depletion every year. And then there is some turnover and inflows of new deep water every winter, almost every winter. You see it skips a few years. But this is exactly the kind of circulation that the Baltzan model is constructed to mimic. So you see that the model performance is pretty good on this. What we have done here is that we looked at the phosphorus. We primarily looked at phosphorus. The model do, as you saw, also oxygen and nitrogen and so on, but we focused here on the phosphorus response. And from the model, we can easily do budgets like this. So we can look at how did it look in the Björnefjärden before the treatment. And we see that there was about 400 kilos of phosphorus in the water column. And the land load is about 200 kilos, according to the time series we have. I know they will do some more analysis on the nutrient inputs, but in the time series we have for the modeling, it's about 200. But there is then a turnover in the sediment. So we have a strong sedimentation of organic matter, and in terms of phosphorus, that is then it's our fluxes. So per year, it's about twice the amount of phosphorus in the water column is sedimented. And almost all of it is released again during the same year, which shows that phosphorus is used many times during the production cycle. So we have a high productivity, and all this sedimentation is also then, here it's phosphorus, but it's also associated with organic matter. And before it's released, so to say, it mineralizes and consumes oxygen. So it's also a source for oxygen depletion. During the aluminum treatment, as Brian said, we bind the phosphate to the aluminum, and it's so to say removed from the system. It is in the sediment, but it's stable in the sediment. So from our modeling results, it seems like even though in this case it's injected in the sediment, some of the aluminum also binds water column phosphorus directly, but it's accumulating in the sediments. So we see that immediately the release of phosphorus to the water column have decreased a lot. And the water column phosphorus in itself is according to the model, about half. However, we also get some import from the offshore of phosphorus that wasn't there before. And this is what kind of main difference between the lakes and the marine environment, that we also have to consider what happens outside our area. So some of the effect of the aluminum treatment is then cancelled by, so to say, an additional load from the offshore. So, and after the treatment, just after the treatment, we see that gradually the amount of phosphorus bound to aluminum is decreasing somewhat. We get new organic matter to the seafloor that is releasing new phosphate to the water column. And the import is still high here. So this is a case like Brian talked about also, that these external loads are still too high, so to say. So the effect of the aluminum treatment is gradually going away. So this is something we can do with models, is that we can make scenarios of this. How long time does it take? Then, I mean, we will see now also, we're following up still if these timescales are exactly these timescales or if they are slightly different. But we can compare then, for instance, this is the amount of phosphorus in the water column. And then we have the so to say, real model simulation with aluminum treatment. But then we can compare with the hypothetical case, if everything remains unchanged in the model, except that we do not do any aluminum treatment. How would it look like then? And then we can scale the difference or the effect of the aluminum treatment in itself. And we see that, especially in the beginning here in 2013, it was actually an event with very high phosphorus concentration, which was due to that these inflow events that I talked about, or breaking up of the anoxic regime didn't happen one winter here. So this is an exceptional event here with very high phosphorus concentration, but the aluminum treatment took away all that phosphorus. And then we see that the effect is then gradually decreasing, and according to the model, it will be only marginal effect on the phosphorus by the end of the 2020s or so. And this lower graph is just showing how much phosphorus is removed to aluminum binding every year during the simulation. This is another graph which involves 4 scenarios with different measures. And it shows total phosphorus, winter mean of total phosphorus, and that is one of the indicators that is used in following up good environmental status in the Water Framework Directive. So there exists a specific level, which is the difference between good and what's called moderate water quality. So to be good water quality, the concentration should be below this line. And what we see here is that we have the white one, still no measures. We have the light blue one is aluminum treatment. And then I added 2 more graphs. The green one is 50% land load. So the load from land is reduced with 50%. and the yellow one is 50% phosphorus concentration in coastal water, which then means that the concentration that the status in the Baltic Sea is close to what we expect from the Baltic Sea Action Plan. And what this illustrates is of course, the aluminum treatment here is very efficient and good environmental status for quite some time, and then maybe it's also natural variability in this, but maybe towards the end, the effect reduce a little bit here. That maybe we cannot be sure that we have good environmental status in that case. But we also see that individually, neither the land load or the offshore measures, so to say, will ensure the good environmental status. So it's a challenging situation in this base. What we see here is one example where it's difficult because the open sea phosphorus concentration will decrease, our projection says, but it will take decades. The local load reductions are in many places challenging, and also there it might be a significant delay, specific, in particular on phosphorus measures in agriculture may take a long time. And then aluminum treatment, we know that, well, it works, but as long as these local loads and open sea concentrations are high, the effect will decrease with time. So it is really showing the challenge of the coastal sea restoration effect. But also, I also want to emphasize, as also Brian talked about, that we can do things with these kind of models to also give an idea about the anticipated effect on water quality of different measures. So it's a little bit trickier maybe to set up models for coastal areas because we have this problem with the exchange with the open sea, but it's still we still can do it, and I think this development here in Björnefjärden, and Björnefjärden is an excellent test basin for these things because it's a lot of things are measured. However, there is also more work to be done. Of course, we that we will look into in the future is also looking into. Now we only talked about phosphorus, but there is also, especially in the marine environment, nitrogen to think about, and that is also very interesting to dig deeper into in Björnefjärden when we have this experiment now reducing phosphorus concentration a lot. What happened then with nitrogen and silica and the plankton community and so on? And I know that the Living Coast project is working on that now as well. So, and I will also say that we made a little fact sheet on these model simulations so far in Swedish. Please, if you would like to have it in English, please be in touch so we see if there is a demand. This is available on our homepage, and if you like a printed version, you could also be in touch. Thank you.
Thank you, Bosse. Very interesting and complex, and there's a strong message from both of you actually about modeling, and we're looking forward to getting back to nitrogen. We'll do that in a later breakfast, of course, then in the future. But let's just stay around Björnefjärden for a short while. You emphasize strongly that Björnefjärden is a very special bay. It's more or less a lake, but there is, of course, exchange with the fjärden outside, I mean the larger part of the ocean. So is this so unique, so it's not possible to do the same kind of treatment in other bays? Are we to look at every bay especially sort of and study it in detail? Or can you draw any general conclusions?
Yes, I mean there are several factors, and I know the study that Brian referred to, they looked into this for lakes, and I think some of these factors are similar for a marine system. It's the effect. First, you need to think about what is the effect you want. Do you want a local water quality improvement, or do you want to remove phosphorus from the system, so to say? Because if you only want to remove phosphorus from the system, you can, I think, do it basically anywhere, just taking into account the correct doses. But if you want to have a water quality improvement, it should be a shallow bay. So you have this contact between the local production and what happens on the seafloor. If it's very deep, you lose that coupling between what's happening in the surface and what's happening on the seafloor. And then the water exchange is very important.
You really stress that, the fact that the sort of phosphorus-rich waters from the outside is coming into the bay. Giving it a more problematic situation, of course. And I want to get back to what you talked about with the external loading, because you and also Brian stressed that if we don't address the external loading, I mean, you can't really do this, really.
No. And I mean, that is also a big question now. With all, I have discussions with the German colleagues that work on problems in the German coast, which is more open. But they still have influence then from big rivers and local and very highly polluted, so to say, rivers in the coastal area, which actually have an influence close to the coast. And there is also the question, could we wait until it becomes good in the open Baltic Sea, or can we do something that has an effect in this coastal area anyway? So it's...
Yes, that was really my next question, because I wanted to ask you, are you actually saying that with good reduction of external loading, you can actually wait and not treat with aluminium? Or is it always a combination?
I think, I mean, it depends. In the coastal setting, as I said before, you also need to consider nitrogen in many places. But then it's also the question is how manageable are your loads and what are your goals? If you have a very economically valuable place, then maybe it's worth to do the aluminum treatment, even though you only have an effect for 10, 15 years.
Okay.
I mean, it's a management issue that we need to.
But that's a good point. Brian, please join us here. And can I ask you the same question, really? Would you say, Brian, then that it's okay to wait and just fix the external loading? Or should one look at these as two methods sort of addressing the same problem?
Well, it depends. Like Wu said, if we need an immediate effect for some particular economic or other reason, and in cases I mentioned in Stockholm where you can't really install measures, they take too much space in the middle of Stockholm, then you can do these types of treatments and expect a longevity of 15 or 20 years and then come back and treat again.
Okay, so that's a key message from both of you, that the effect will sort of be reduced after a while, and you need to plan for further reductions and further treatments later on. Thanks so far. We have of course had questions here. One that is talking and asking about effects on vegetation. We had a very long, interesting question coming to us already yesterday, but in essence, if I should shorten it, it's about effects on the vegetation and in lakes then. Brian, can you say something about this? Has this been studied?
Yes, we know quite a bit about this, and this is a tricky, not a tricky restoration topic, but a tricky lake user topic. Either we have algae in lakes or macrophytes, aquatic plants.
So for us who aren't marine biologists, what's a macrophyte? Can you give us, the common word instead?
It's an aquatic plant, a plant in the lake, growing in the lake. So when we have these eutrophic conditions, the plants don't grow. There's not enough light for them to grow, whereas they were growing quite a bit before eutrophication occurred. So when we do an aluminum treatment, we clear up the water and much more of the sediment bed is available for growth of plants. So we're adding light, which is basically fertilizer, to the sediment bed and plants start growing again like they used to. However, if you like to fish or swim or canoe, in particular in shallow lakes where there was very low light availability, the plants will come back. And of course, then you think that this restoration didn't work because you like to use the lake for that particular reason. So the expectations, I think, are important before we go in and do these treatments. It all depends on your viewpoint and what you use a lake for.
Okay, so we're getting back to what you both of you stress, your goals and what is your expectations from this treatment. All right, thank you. And we also have a question here regarding aluminium. You stress, Brian, that it's not a chemical, it's a mineral, and it's a mineral treatment. But I think we all are aware of that people in general think about aluminium as toxic. And, you know, there is a toxicity aspect of aluminium. How is your views on your response to citizens who are worried? Do you come across this a lot? Are people worried?
Yes, all the time.
All the time, all right. And what do you say to them then?
Yeah, particularly here in the Nordic areas with regard to acidification. When pH is under 6 or greater than 9, either you have an acidic lake or a very high pH lake, aluminum can become soluble, so that mineral dissolves. But when we're looking at eutrophic lakes, they're often around pH 7, 8, and then that aluminum is in a mineral form. So, but if it is in a soluble form, it can cause issues. For example, it sticks to fish gills and they can't breathe, and it causes some other obviously not good issues. So we don't want to go in and aluminum treat acidified lakes, but those lakes typically don't have enough phosphorus. Okay. But when we're looking at eutrophic lakes, the pH is in a neutral range, and then you have formation of this very hard, permanently phosphorus-binding mineral.
Okay, thank you. And here is just a clarification question to Bove. It's asking whether or not it was correct that your last illustration looked at aluminium separate from land load and coastal load. If so, how would aluminium and land combined turn out?
Well, it's approximately additive, I would guess.
Additive, okay.
So,
but it was correct. You looked at them separately. Yeah, okay.
Yeah.
So we can send some more information.
Also, and just a little point about these landloads and so on. There are some crucial differences between the Baltic Sea as a whole and Björnefjärden. And one of the things is that it doesn't take 30 years for landload to have an effect in Björnefjärden. In a few years, you have full effect from landload reduction.
So it really pays off well in such an area in relation to how long you need to wait for effects in the Baltic Sea.
Yeah. Of course, the natural variability is also larger when it comes to the loads, because if you have just a heavy rainfall, it will impact in one place, will impact the whole bay, of course. So that could shadow some improvements. But it's important to note that these timescales are different on these scales. It's not because simply, as you saw, the phosphorus load is approximately of the same size as the whole phosphorus water column pool. But in the Baltic Sea, it's a difference of a factor of 30 or 20. So that is a big difference.
We have more questions. We don't have time for all of them, so we will get back, as I said, on our web. But a final question to both of you. What would be the most important advice you would like to sort of address to planners who are looking at dealing with either their lake or the coastal area and thinking about how shall I go about this? What's your advice? Brian, please go ahead first.
I would say proper modeling of the system. If you don't know what your sources are and which sources of nutrients you should control, you're just guessing, and you're going to most likely end up wasting a lot of money that could be spent on fixing more lakes.
Yeah,
Thank
and
you.
I agree. Maybe also add to be really go in and discuss a little bit of exactly what your objectives are.
Yeah,
as
right.
well.
Okay, so objectives, clear water or more fish or whatever it is. Okay.
Expectations, I think, are important
Expectations.
too.
Thank you. Thank you so much. This has been most interesting. And thanks all of you who are listening. I will now give a short advertisement of the next Baltic Breakfast. It's coming up pretty soon on the 30th of November, just at the end of November. And this will also be in English, but we will be at the hotel close to Hötorget in Stockholm, Scandic Klara. You can just check that on our web. But it's going to be broadcasted as well, naturally. And then, since the convention on the biodiversity is coming up in Montreal in December, we will hear researchers talk about the hot topics of the convention. It'll be about marine protection and marine genetic diversity. So please join us then, and until then, have a nice November. Thank you.